have a question and answer utility that you could use to ask any technical questions or any questions about the material being presented. The questions will be answered by Nick Petrosky. If you have any issues with the audio cutting out or any slides that are not showing up properly, you could address your concerns to Allison Oba using the chat box. Just a reminder that this webinar is also recorded and will be available on our website within a few days. If you need a copy of the slides that are being presented, you could email Allison Oba. Her email address is allison.oba@arisafety.com. Before we get started on our webinar today, just a quick recap on a previous webinar. We talked about safe workstation. In this, we discussed safety and the need for safety around workstations. We'll discuss some shock hazards that are potential shock hazards when you're working in a high voltage environment, and also the effects of current on our human body. We then discussed the operator and the 10 things an operator should know when performing high-pot testing or any kind of electrical safety testing. Then we looked at the buildings, safeguarding the stations with positive protection and without positive protection. And we also looked at additional safety measures that could be enforced around the workstation. If you need to review, or if you would like to go over this webinar, it's available on our website. For today's webinar, we have ground bound and ground continuity testing. What we're going to do is define both ground bound and ground continuity testing. But before we get started, we want to define what a ground is and what it means to have a product electrically grounded. We'll go over the definition of Class 1 and Class 2 products, with majority of electrical products fall under these two categories, and we'll clearly define which class product needs to have ground bound or ground continuity tested. We'll then look at the actual ground bound test. We'll define ground bound test, what it is. We'll look at the standards, and we'll look at what the parameters are for the ground bound testing. We'll also show you some example of the actual ground bound being performed on a DUT or device at the test. Next, we'll look at ground continuity. We'll define the ground continuity, show you some examples, and also look at the standards for the definition of ground continuity. And later, or almost towards the end, we'll also compare and contrast ground bound versus ground continuity. We'll also show you a video that shows you a ground bound, a ground continuity that would pass, but a ground bound that would fail. This will be a live video. We'll show you at the end of almost towards the end of the webinar. Before we get started, we do have some poll questions throughout the webinar. So we have a first poll would be asking you a question about what kind of test you're performing. Before the poll, we want to make sure you understand the difference between type testing and routine testing. So taking a look at here, a type test would be what a prototype test will go through. It will be something in your lab that you're performing tests on, or doing any conformance testing. A routine test would be a production line testing that all your products go through, or this is doing an assembly line or a final assembly. So we'll put up the poll, give you some time to respond to it, and go over the results with you.
Hi there, Bashan. We had a good response today from our poll question. How do you perform ground bond and or ground continuity tests? We asked you to select all that apply. 35% of people say they perform ground bond type testing. 26% of people say they perform ground continuity type testing, and 53% of people perform ground bond and ground continuity type testing. 38% of people perform production ground bond testing. 32% perform production ground continuity testing. Thank you all for participating.
Again, thanks for the participation, guys. And we have the results are pretty. The 53% of ground bond and ground continuity testing, that shows that half of the people are testing in the lab environment, both ground bond and ground continuity. During production, there's the ground continuity is 32%. We'll go over next. We want to go over what is ground, the definition of ground. A ground acts as a reference point for any electrical circuit. When you have a product that's rated for 120 volts or a certain number of voltage, you want to apply a voltage to it that's 120, but it needs a reference point. So the ground acts as a reference point for this voltage that needs to be applied. Ground could also act as a secondary line of defense against electrical shock. Your first defense would be the insulation on your current carrying conductor. In event of a failure of the insulation, ground would act as a secondary defense. Ground is also a common return path for electrical current. For purpose of our webinar here, we're going to be concerned with the ground that has that reduces the risk of electrical reduces the risk of electrical shock. Just a quick overview here about modern power distribution. As you can see on the left side, a normal operating system where the power is delivered by the utility company, but via the utility station. The power is routed to your house. Any electronics powered on in your house would draw the power and operate normally. In an event of a failure, on the right here, if there was an insulation breakdown in the house, and if the line had shorted with a metal cabinet or metal chassis somewhere, now that potentially raises the risk of somebody coming in contact with this metal point, and electricity would always take the least resistive path to ground. So if a person touching this point provided a path to ground, they will be in for a major shock. That's why having a properly grounded system helps reroute this fault current straight to ground and not through the human body. We also want to define there's two different types of ground. So a service ground is where with service utility coming into the building, this is to protect your products, your machine, your tools, and basically anything from damages. The service grounds are also at the generator and also at the service utility stations from the power company. The second type of ground is equipment ground, and that's what we're more concerned with. The equipment ground is what protects the operator. The major difference between these two is service ground will protect items, and the equipment ground is there to protect the operator or the end user of your product. So most of the electrical products fall into two different kind of categories. You've probably seen either class 1 products in your household or class 2 products or a combination of both. To go over these, class 1 products is your normal line cord that terminates in 3-prong line cord. It has a line, a neutral, and a ground. The ground prong is connected to the chassis of your product, and this provides a ground path for the fault current to take in event of an insulation breakdown. And like I mentioned earlier, this is the secondary defense. So first would be your insulation, and the second protection is your ground cord. Class 2 products are double insulated products. So again, we're looking at two layers of protection. First layer is the first insulation, and the second layer is the second insulation. The class 2 products are tested with a higher HIPOD test to make sure the insulation does not break down. The testing we perform ground bond would be majority of our product would be class 1 products, and that's why the poll results showed that when you're if you had a product that's a class 2 product, you're not required to perform any ground bond or ground continuity tests, as there's no ground on your class 2 product. People that did enter production line testing for class mostly would have class 1 product, or have a product that the standards requires for them to run a ground circuit ground bond test. So what defines a good ground? We'll look at the National Electric Code that specifies what a ground is, but the National Electric Code gets the information from the National Fire Protection Agency, which is adopted in all 50 U.S. states. This NEC code, NFPA 70, provides a good reference for what a good ground is. If you look at the definition for NEC 250-45, is mentioning any exposed non-current carrying metal of the cord or plug connected equipment which may become energized shall be grounded. So what this means is that you want your product that has any metal accessible part by a user, or any type of metal that could come in contact with anybody, needs to be at a zero reference or zero ground, at a ground point potential. So that's why we recommend that any accessible part be grounded on your product which has a proper ground through the power cord. The second definition comes from NEC 250-51. This is where the main definition of a ground comes. It needs to have a permanent and continuous path. This path also needs to have a current carrying capacity to conduct, in case of a fault current, to be able to carry the fault currents. What this means is if there is an instant where there's fault current occurring anywhere from, let's say, 10 amps all the way up to 40 amps of current going through it, this ground circuit should be able to handle this current. Also, a requirement is low impedance. This means that the ground should be always the lowest possible impedance to ground. This avoids the electricity taking the path from any other form. And we'll look at the standards that define the actual impedance depending on the product itself. Before we go on, since we're going to be discussing a lot of the standards involved, we do want to ask a second poll. This will ask what standards you're confirming to currently, and please participate in the poll. Thank you.
All right, everybody. Again, thank you so much for participating in our poll. What standard to which are you testing? I'm going to close the poll and share the results. And it looks like 26% of you test to 606-01-1, third edition. 9% of you test to 60335-1, fifth edition. 21% of you test to 60950-1, second edition. 29% of you test to 61010-1, third edition. And 15% of you test to other, but I have not gotten any responses in my chat box, except for Larry, who said he tests to UL 508A. Thank you so much for participating, guys.
Thanks, Allison. Thank you guys for participating. Looks like there's an even split between medical testing, also household appliances. I'm sorry, not medical testing, laboratory equipment, and also IT equipment. If you are testing with any other UL standards, if you wouldn't mind typing that into the chat box, so we would know what kind of UL standards you're testing to. If you do require any assistance on going through the standards, we have resources. We have all the standards available on our end that we could review, and you could contact either myself or Nick Petrosky, and we'll get you some help and resources on looking at your UL standards or the standards you're conforming to. All right, so let's get into the ground bond and ground continuity test. The reason we want to define ground bond and ground continuity is the standards don't always specify if they're saying ground bond or ground continuity. Let's go over the purpose of why we do the ground bond or ground continuity testing. As I mentioned earlier, is to ensure that there's less risk of electrical shock. Having a properly grounded system will provide this proper ground for the fault current to carry it to ground. The way we test this is we apply high current to the ground circuit, and in order to test to see if the ground circuit is capable of carrying the fault current. We measure the potential difference of the voltage across the ground circuit, and in result this gives us the resistance value. And like I said earlier about the National Electric Code specifies that it needs to be low impedance path to ground. Some of the standards do specify 100 milliohms as the impedance for the ground circuit. Anything higher would not conform to those standards. And we'll go over the next slides. Taking a look at how a ground bond test is performed. On the left, you see a Omnia series tester. It's one of the 8204 tester. It's connected to a universal adapter box. This adapter box provides you to perform multiple tests. And what we're concerned with doing the ground bond test, but this adapter box will also let you do a high pot test. As you could see, the adapter box is connected to the two red connectors, which provide the high current. This high current is injected onto the ground pin, which would be the round pin of the fan. And then the current is rerouted back to the instrument to check for the impedance or the resistance to ground via the black return lead, which is connected to a single black lead at the bottom. And for the high pot test, which could be performed, is connected to the white with the red circle, is where the high voltage is outputted. So this product could perform a high pot test along with the ground bond test. So in the circuit diagram, what we just discussed is on the left side we have our tester outputting high current on the ground pin. So during a ground bond test, only item we're concerned with is the ground pin. Now this ground pin is connected to the product chassis, and our return point is connected to the product chassis also. There's a resistance value between the ground pin and the return, which was shown as the resistor in our DUT, which is on the right side. One thing I want to mention about the Cohen connection is we also our instruments also have what's called Cohen connection that the connection will has a sense plus and a sense minus. This connection helps you with the voltage drop across your leads to negate that voltage drop. In essence, you will be testing, having a Cohen connection at the DUT, you are testing the product at the DUT itself. So in this case, at the chassis of your product is where the real measurements are being made if you're using the Cohen connection. Let's go over a pass condition. The high pot tester or the ground bond tester on the left is outputting high amps, anywhere range for 15, 20, 30 amps, and this current is passed to the ground circuit of the DUT, which is on the right. And if the return path, if the instrument is measuring the return current along with the resistor value of the ground circuit. If this circuit or if the ground path is present and the resistance is less than the set value, this condition will be a pass condition. And when we look at the standards, we'll look at the actual resistance value for your ground circuit. Let's discuss a failed ground bond test. When the output on the instrument is outputting high current, if there is no return path or if the resistor value is too high for the ground circuit, the tester is going to report a failure message. In this case, either there was a ground that burned up under high stress, or there was the resistance of the ground values are too high for your settings. let's quickly take a look at standards. These standards were part of the polls, the 60601, the medical device testing. If you look at the section for ground bond testing, would be this called impedance and current carrying capabilities. The requirements for this is you want to output, you need to have a unit that could output 25 amps of current, or 1.5 times the highest rated current, whichever is greater, plus or minus 10%. This amount of current needs to pass through the ground circuit or the earthing circuit, and other requirements are the no load voltage to be less than 6 volts. What this means is you could set your test parameters to output at 6 volt at 25 amps or 1.5 times the highest current rating. The frequency will be depending on the DUT that's being tested. If the DUT operates normally on 60 hertz, it would be 60 hertz requirement, of course, and if it's 50 hertz, you'll select the 50 hertz. The pass criteria is the important thing here. It requires that the earthing circuit be less than 100 milliohms. Now, this is going back to our when we're applying a high current to the ground circuit or the earthing circuit. This impedance to ground should be less than 100 milliohms. You might also have products that have non-detachable power supply. For this instance, the standards does allow you to have a little more leeway where you could have 200 milliohms of the impedance could be as high as 200 milliohms. Next, we'll take a look at UL 1598. This is for luminaries. This is UL 1598 3rd edition. The requirements here are just a little different. It does require 30 amps of current, and this current needs to be passed between earthing contact and the accessible conductive part. There is a different voltage that's allowed here. You are allowed to go up to 12 volts, either AC or DC. But main item to note here will be the test time. This test time is for 60 to 120 seconds. What this means that the ground bond test needs to be ran for at least 1 minute and see if it's able to carry that much current for at least 1 minute. The pass criteria is for impedance to be less than 100 milliohms, just like the other standard, but there is no exception for the line cord that already has attached line cords. And we're still talking about all of the type testing here. We're going to look at some household IEC 60335-1. These are the household appliances. If you took a look at here, it calls for provision for earthing test, similar to AC ground bond test. Again, the current here required is 25 amps or 1.5 of the highest rated current. Sometimes the highest rated current will be your the fuse on your panels, or for the power coming into the building or the unit that's providing the power. Also, the voltage on this is 12 volts AC or DC. Again, the impedance, which is the major factor here, needs to be less than 100 milliohms. I do have a quick video here that shows you how a ground bond test is performed, and this shows you a product that's being tested for ground bond at 30 amps. This is one of our high amp tester. You can see that the setting is for 30 amps. This overview shows you the adapter box, the product itself that's going to be tested, and also the leads. We have the regular current that is outputted through that big connector, the red connector, and your sense connections for Kelvin measurements. We're going to also attach the return lead to our tester, which the current will flow back to, and this will be the black return lead. The black return lead also has the sense minus, which makes sure the measurements are made as a Kelvin connection. The product here you can see has an attached cord. The return would be clipped onto a good point on the product, a good ground point on the product, normally a ground lug or a chassis point, and the power cord is plugged into our universal adapter box. When the test is ran, the current will be outputted on the red wire, and the return is taken on the black return lead. As you could see, this currently the product passed the HiPod testing. Next, we're going to take a look into the ground continuity test. What a ground continuity test is just a simple test that applies a small DC current and checks for a continuous path. A major difference between ground continuity and ground bond is that the continuity is only checking for a continuous path. It does not check for any capacity of the wire to carry any kind of current or any kind of impedance value. The ground continuity could be also performed with a simple light buzzer combo, which provides you a go no-go signal either with a light or a buzzer that shows you there's a continuous path between 2 points. The ground continuity needs to be also performed on the ground or the earthing circuit to make sure there's a continuous path to ground for any fault current to be carried. Taking a look at the standards for what the continuity test, when they're saying routine tests, these are routine tests for your production line. These do call out for a continuity test to be ran on your protective earth circuit. There's no current specified, so simply means that any kind of continuity test will conform to your standards. Taking a look at the household appliances standard, IEC 60335-1. If you look at the routine test Annex A section, you do see there's a current specified. So this becomes a ground bond test instead of a ground continuity. As we saw previously, there was no current requirement here, and this was referring to a ground continuity test. Here, if you look at the routine test, it asks you to perform a 10 amp current test and making sure the impedance is less than 200 milliohms. For cord connected equipment, anything else, the appliance is again less than 100 milliohms. We'd like to go over some major differences here between ground bond and ground continuity. What ground continuity is doing is just making sure there's an existing connection. Majority of the time, the resistance value of the ground continuity is usually in the ohms range. This is a quick test and easy to perform. And majority of our HiPod tester at AR do have a built-in continuity test that could indicate a good continuous path. When we move on to ground bond testing, this is the test that actually verifies the connection that's made to ground is able to carry the fault current. The impedance for this patch needs to be less than a certain amount, usually given in the milliohm range. This also provides ground bond test is for your safety of the operator or the end user, and this is where the fault currents are carried. In the event of a fault, the fault currents are carried to ground, and this ground bond test verifies that your product is capable of carrying this current. Let's take a look at what this means. When we have a ground bond versus ground continuity, if you have a cable that is damaged in a certain way so this is a 64-strand cable, and let's assume that there's some kind of damage through production or basically some kind of damage that you can't see, and only one strand is connected in the wire. If you take a look at this, and if you only run a ground continuity test, if this is in your production or in your lab environment, the ground continuity test is going to pass, even though because there's only one strand and there's a continuous path, the ground continuity will always report a pass. Now, if you put the wire through its paces and do a ground bond test and run some kind of current through it, the wire, the single strand would actually burn up and open up the wire. In this case, then you will have a faulty ground. do have a quick video here that I could show you, a quick demonstration here. This will demonstrate a ground continuity test being performed on a single piece of wire or paper clip in this instance. And then also we're going to be performing a ground bond test. So let's take a look at this video. As you can see in the video, the ground continuity is set for 10 seconds. The high limit is for 3 ohms. So anything higher than 3 ohms would fail the ground continuity test. Our ground bond settings are 40 amp current. The voltage is set to 6 volts. In this case, we have set our high limit to 150 milliohms. And again, we're going to do a dual cycle for 10 seconds. Once the test has started, the first test is the continuity test. And since it's a paper clip, it's a continuous path, you'll get a pass. The next test is going to be the actual ground bond test being ran. And currently is running the continuity test, which you should pass. And as you could see, this paper clip or a strand of wire is not capable of carrying 40 amps of current. Now, if this was inside of your product and the product was damaged, the ground bond test would be the one that would catch this the strand of wire and actually burn up the strand of wire. That brings us to the conclusion of our ground bond versus ground continuity. I did want to go over quickly about what was mentioned in previous webinar. We have audit survival guide that could be if you would like to receive one of our documentations or resources on audit survival guide, please check your chat box for the links to the web page. And this is to make your compliance safe and easy, and it has a lot of pointers for you to how to survive an audit. There's also information on IQ, OQ procedures, and if you'd like more information, please contact one of us and we could provide you more information, or follow the link on the website. Lastly, I want to provide the contact information. If you, like I mentioned earlier, anyone wants a copy of the presentation, could contact Allison Oba at arisafety.com, or you could visit our website for any previous webinar that was done this year, and we have a list of all the webinars up from last year. I would like now to open the floor for any questions that anybody might have about either ground continuity or ground bond testing, or any other questions pertaining to high-pot testing, or any UL standards or any kind of standard information.
Hey, Bashan, nothing yet, but I'll keep you posted.
All right, thank you, Nick.
Well, it's not a question, but somebody just said good job.
All right, thank you, guys. We do have more webinars coming up. We try to do each webinar, at least one webinar each month, so we'll send out the links for the next webinar. We do go into details on each and every type of test for electrical safety testing, and also provide a lot of other resources. So look forward for future webinars, and thank you for attending.
Hey, Bashan. We do have
Yes.
one question here. Somebody was curious about what is IR versus ground bond.
Sure. All right, so insulation resistance is actually when you're applying high voltage to your line, neutral, connector, and measuring to ground. So in essence, what you're doing is having your normally current carrying conductors, which will be a line and neutral, you're putting them at a higher potential, and you're measuring the resistance between that and the ground plane. So if our IR measurements are always want to be really high, indicates a good insulation between your normally line carrying conductor versus your ground plane. A ground bond test does not involve anything to do with the actual line or neutral. It's actually just testing your ground circuitry on your ground pin. You're applying high voltage to your ground pin, taking the return on your either the product chassis or the return on your return lug, or the product chassis or the ground lug on the back of the unit. So the main difference would be you're actually applying high voltage, in essence, of 500 volts or 1,000 volts, depending on the standards when you're performing IR tests. A ground bond test is more to do with current carrying capacity of your ground circuit. The current carrying capacity is measured, of course, when you're passing high current through the ground circuit. I hope that answers the questions. If not, do let us know.
Looks like that's about it, Bashan.
Okay. All right. Thank you guys for attending, and see you next time.